Geoengineering, the deliberate large-scale intervention in the Earth's natural systems, represents a profound frontier in our response to a warming planet. As global temperatures continue to rise, the urgency to explore all viable options intensifies. This field offers a spectrum of technological approaches, each with unique potentials and challenges. It compels us to consider how human ingenuity might play a role in stabilizing our climate. One major category is solar radiation management, or SRM, which aims to reflect a small percentage of sunlight back into space. These methods do not remove greenhouse gases, but rather seek to reduce the amount of solar energy absorbed by the Earth. The goal is to achieve a rapid cooling effect, potentially mitigating some immediate impacts of climate change. Stratospheric aerosol injection, or SAI, is a prominent SRM concept. It involves injecting reflective aerosols, such as sulfur dioxide, into the stratosphere to mimic the cooling effect of large volcanic eruptions. While offering the potential for relatively swift temperature reduction, SAI presents significant uncertainties regarding regional climate impacts and potential disruptions to weather patterns. Other SRM approaches include marine cloud brightening, which involves spraying sea salt particles into clouds to make them more reflective. Space-based reflectors are also conceptualized, though they represent a far more complex and costly endeavor. The primary benefit of SRM is its potential for rapid global temperature reduction, but it does not address the root cause of ocean acidification. The second major category is carbon dioxide removal, or CDR, which focuses on actively removing carbon dioxide from the atmosphere. Unlike SRM, CDR addresses the fundamental cause of climate change by reducing the concentration of greenhouse gases. These technologies aim to reverse the accumulation of CO2, offering a long-term solution. Direct air capture, or DAC, is a technology that chemically filters CO2 directly from ambient air. Once captured, the CO2 can be stored permanently underground or utilized in various industrial processes. DAC plants are currently operational, demonstrating the feasibility of this approach, though scaling them up remains a significant challenge. Bioenergy with carbon capture and storage, or BECCS, combines biomass energy production with carbon capture technology. Plants absorb CO2 as they grow, and when burned for energy, the emissions are captured and stored. This method offers the potential for net negative emissions, but it raises concerns about land use, water resources, and biodiversity. Enhanced weathering involves accelerating natural geological processes that absorb CO2 from the atmosphere. This can be achieved by spreading finely ground silicate rocks on land or in oceans where they react with CO2. While promising, the effectiveness and environmental impacts of large-scale deployment require further research. It is crucial to understand that geoengineering technologies are not a substitute for aggressive emissions reductions. They are best viewed as potential complements, offering additional tools in a comprehensive climate strategy. Relying solely on geoengineering without significant decarbonization carries immense risks and moral hazards. The deployment of geoengineering technologies raises profound ethical, governance, and geopolitical questions. Who decides when, where, and how these technologies are used? What are the potential unintended consequences for specific regions or ecosystems? These are complex issues that demand international cooperation and equitable frameworks. Thorough research, transparent governance, and public engagement are essential before any large-scale deployment. We must carefully weigh the potential benefits against the risks, ensuring that our interventions are well-informed and responsible. The scientific community continues to explore these avenues with caution and optimism. Geoengineering offers a fascinating glimpse into humanity's capacity for technological innovation in the face of existential challenges. From the rapid cooling potential of solar radiation management to the long-term atmospheric cleansing of carbon dioxide removal, these technologies present both hope and complexity. As we navigate the urgent realities of climate change, continued research, open debate, and a balanced perspective will be vital. Our collective future depends on a thoughtful and integrated approach, combining emissions reduction with the responsible exploration of all viable climate solutions.